Floyd-Warshall algorithm. For the case, if you have to find the shortest path between all pairs of the nodes. In the extra, we can only find the shortest path between a single source node to all the other nodes. But Floyd-Warshall's main advantage is we can find all pair shortest path. So how does it work? Let's see. Consider here V is the set of all the nodes. Let's first consider a subset of V. That is the nodes. Pij is equal to V1, V2 from 1 till k, all the set of vertices. Now Dij subscript k is the weight of the shortest path from node I to node j that includes one of the vertices in from 1 to k. Like here k denotes the intermediate nodes 1 to k from which we can pass on through to reach the destination j. Let's suppose if the node Vk is not in the shortest path from node I to node j, then the distance between I to j will be equal to the previous iteration distance between I to j. Otherwise, if node k is in the shortest path, then the shortest path between I to j is equal to k minus 1 iteration distance from I to k plus distance from node k to node j in the previous iteration. Now this leads us to the following recurrence formula, which you can see that distance I to j in kth iteration is equal to Aij. Aij is the weight of the node if I to j, if k is equal to 0, if it's the first iteration or 0th iteration, or else if k is greater than equal to 1 of the first 1th or more than 1th iteration, it will be the minimum between distance from node I to j in the k minus 1th iteration, or distance from I to k in the k minus 1 iteration plus from k to j in the k minus 1th iteration. We can also implement this using iteration. We do not need to implement the recursion formula here. So as you can see, this is the main pseudocode of our algorithm. Its time complexity will be O of n cube. Although we don't need n copies of the D matrix, we only need one, but as we can use parallelization using many processors. In fact, we will only use only one matrix here. So how will the D matrix or the adjacency matrix will be partitioned? As you can see on the screen, we will divide the D matrix into p blocks of size n by root p. N is the number of parallel processors we have. So each processor is responsible for n square by root p elements of the D matrix. However, we still need to make a communication between all the processors so that they can exchange the data. As you can see, the communication pattern is like this. Analysis. Now let's analyze the time complexity and space complexity using a Floyd algorithm if we use parallel computing. So each processor has to send its data to all the processors on the same row and column. If we use a broadcast message, then the time communication complexity will be O of n into log p divided by under root p. The synchronization step requires O of k log p. To synchronize the whole process, we need a time complexity of k log p. And each processor to compute all the values, we will require O of n square by root p time complexity. So total time complexity for each step becomes O of n square by p plus O of n log p divided by root p. And finally, the complexity for n steps will be of the k loop. For computation, we will require O of n cube by p. And for communication, for broadcasting, for exchanging data, we will require O of n square log p by root p. So what are the applications of shortest path parallelization? It can be used for real-time routing with traffic data in Google Maps, Apple Maps, or to compute NPC movement or path planning. We can implement this parallel process into the AI model of NPCs and other players. In social networking, we can use it to optimize the influencer search or connection discoveries. We can also use this in data centers for efficient routing and load balancing.